Hey ENGG1200, today I'm here to talk to you about torque and explain the concept to you. So torque is force times distance, okay? And that distance is the distance from the centre of rotation, or more specifically, the centre of gravity. So I'll just use this door as an example. It rotates around here. So if I press with the force, the same force, closer towards the centre of rotation, my torque is going to be less. So it's harder to close the door here than if I close it here where the distance is much greater. You increase the distance, you increase the torque, or if you increase the force, you increase the torque. There's two types of forces, static and dynamic forces. And like that, there's also two types of torques, static and both dynamic torque. For this assignment, you'll be dealing with static torque. And it's the same, and it applies the same concepts as static and dynamic forces. So with a dynamic force, the energy from the force is converted into motion. I'm applying a force here, and it moves the object. However, with static forces, there's a restraining force and an applied force, and the energy from the force goes into physically deflecting the material. And as you'd know from Hooke's law, F equals kx. Now the same applies to torque. When a torque is applied, being my hand in this case, and there's no restraint, the torque is converted into motion, like this. Now, in the case of when there is a restraint, and a torque is applied, the energy goes into physically deflecting the material, like this. So here we have the two equations for stress and for stress for both torque and force, and normal force, tension force. So this stress formula here is given in your project brief, and this one here is what you would have seen in your materials classes. So stress here is simply force divided by area, area being the cross-sectional area of the material that's under stress. Now, something important about this is that the stress is uniform throughout the whole material. Now I'll show you how stress is very similar when it's applied from torque. So stress here, this torque, which is, as we know, torque is equal to force times distance. So this torque here can be considered the force. And this IP here is something called the polar moment of inertia. Now that can be considered fairly similar to the area. Now this polar moment of inertia can be found on readily available literature on the internet. Now there's one difference between this type of stress and this type of stress. Here we have an R term, which is simply the radius of the shaft under torsion. Now what this says here is that the stress varies linearly throughout the shaft. So what this means is at the center of the shaft, the stress is 0, and at the edge of the shaft, the stress is the maximum. And this is the stress we care about, this maximum stress. Now we'll have a look at the displacement. So this displacement is also given in the project brief, and its displacement is in terms of theta, which is the angle of rotation of it, as we saw before when I applied a static torque. Now the displacement for a normal force is given by the strain equation, change in length divided by length, which we've seen from our materials prac. Now I'll show you how the displacement is also similar in both scenarios. So here we have strain as change in length over length, and you'll also remember that the Young's modulus is equal to the stress divided by the strain. So this means we can now write strain, which is equal to change in length divided by length, is equal to the stress, which is force over area, divided by the Young's modulus. So what that means is change in length divided by length is equal to force times area over Young's modulus. So that means our change in length is equal to our force times our length divided by our area divided by our Young's modulus. So it's force times length divided by area and Young's modulus. So now if we move over here to torque, you can see something similar. Torque, which is force times distance and can be considered our force in this situation, times the length of the object that we're stretching, times by something called the shear modulus, divided by the polar moment of inertia. So the shear modulus is essentially the Young's modulus, but for a torque scenario. And the polar moment of inertia is essentially the area, but for a torque scenario. So these are very similar equations, and it's just simply the coordinate system that we've chosen. In this side we're working more in polar coordinates, whereas this side over here we're just working in normal Cartesian coordinates. So there's lots of similarities between these two. Are there any questions?